Okay, lecture 81, measuring pressure. So last time we talked about Pascal's principle and also mechanical advantage in hydraulics. Today we're going to talk about how to actually measure pressure. And so what I've drawn on the board here is called, well, I think it's just called a simple barometer. Okay, it's used to measure atmospheric pressure. Now, though the atmosphere is a gas, and we haven't talked about gases yet, you do understand that it exerts a downward pressure, well, actually a pressure from all directions on us because of the weight of the air above us, yes?
Yeah.
So this is a device that was built to measure that pressure. I don't remember who was the first to build it, but the idea is you can get a glass tube, and you can fill it with a liquid, okay? You might imagine, like, laying the liquid, pour the liquid into the tube, turn it upside down a little bit, right, so that you can get the liquid to run all the way to the bottom. You let it fill up for a bit, and then you slowly tip it back, right? And as the liquid withdraws from up here, right, this area above it will be largely evacuated, okay? And so the pressure up there will be zero, okay, because the air won't be there, supposedly, right?
Yeah.
So that's the general idea here, is that up in this evacuated region you have zero pressure, okay? And on the other end is an open tube, okay? So you'll have a pressure pushing down. Now if we cut the top off of this, right, you'll recall that the levels of the liquid would balance out. They would be the same, right? As they stand now, though, we have a delta H, the difference in the height of the liquid on one side versus the other, right? So imagine starting this pressure over here out at zero. They would be completely balanced, the two liquid levels. And as you increase the pressure, it pushes the liquid down and creates this separation between the two liquid levels, right? And from yesterday, we had that delta P over delta H was equal to rho times G, where rho is approximately constant at all pressures for a liquid. And G is the acceleration due to gravity, right? The little gravitational constant, I guess you call it, 10 meters per second per second. If you were to solve this for delta H, right, you would get that delta H is equal to delta P divided by rho G. Yes? And so depending on what liquid you put in here, right, will change the density, right? So a larger density will create a smaller displacement, right? So the difference between these two heights will be smaller. If you use a larger density liquid, a smaller density liquid would have a larger displacement or imbalance, okay? So for example, if the liquid here is mercury, and mercury is a good choice, it's a liquid metal, okay? Unlike oxygen, you're not going to get gas like air and nitrogen bubbling up through the liquid to try to, right, restore a balance of oxygen levels in here, right? The fact that there's no pressure here, there's a lot of pressure here, almost forces oxygen and other gases through the liquid to rise up in there and fill that cavity, that evacuated region, right? But I think probably one of the reasons they chose mercury is because I don't think mercury will allow that to happen. Also, they chose mercury because the density is very large. So rho for water, as you recall, H2O, is equal to 1 kilogram per meter cubed. That's the density, right? What is it for mercury? Mercury is, we'll just call it 13.6. For mercury, it's 13.6 kilograms per meter cubed, right? So a little over 10 times as dense, right? So that means that you can have a more compact barometer, okay? The pressure of the atmosphere, okay? There's many different units for pressure, by the way. Okay, and I'm not going to cover all of them, but I'll cover a few. But one is 1 atm. That's 1 unit of atmospheric pressure, right? Remember that we measure pressure in newtons per meter squared, okay? But I didn't tell you that 1 newton meter squared, whoop, I'm sorry, that's 1 over newtons. 1 newton per meter squared is equal to 1 Pascal, after Blaise Pascal, Pascal's principle that we talked about last time, right? So the standard unit of pressure in SI is newtons per meter squared, but that's also equal to 1 Pascal, okay? Make sense? So just like joules, right? We give it a special name, so we don't have to say newtons per meter squared. We can just say pascals, okay? But 1 atmosphere is equal to 101.325 kilopascals. Right, so it's about 100,000 pascals, okay? That's atmospheric pressure, right? So the 1 Pascal, I forget what it is. I think it's something like it's the pressure you would feel by laying a dollar bill on your hand or something like that. It's not very much, 1 Pascal, okay?
Okay.
So the atmospheric pressure we experience right now is about 100,000 pascals. So using this formula here, right, we can calculate what delta H is. So delta P, if P in here, if the pressure inside the evacuated portion is 0, then delta P is just P minus P naught, or well, I guess this is P naught. It's P naught minus 0, which is just P naught. So we'll write P naught over, we'll use mercury, rho of mercury, and then G is just G. And so what are these values? So we have 101,325 newtons per meter squared, right? Divided by 13.6 times 10 to the 3 grams per meter cubed, and then times G, which is 9.81 meters per second squared. I think I got all of that right. And when we evaluate this, this evaluates to approximately 760 millimeters. Okay, so 0.76 meters if you want. Okay? And so another unit of measurement, 1 atmosphere, is equal to 760. And the way they write this is millimeters of mercury, like so. Okay? So they're measuring pressure by just giving you the displacement, okay, in millimeters. Why millimeters, I don't know. But, yeah. And this is also equal to 760 torr. That's an O, not an A. Fix that. After an Italian scientist named Torricelli, who probably was the first one to make these measurements, I guess. So 1 torr is 1 millimeter of mercury, right, obviously. So 1 atmosphere, 760 millimeters of mercury, 760 torr. If you wanted it in terms of water, right, a better unit to use might be inches, right? I believe it's at feet even. I believe it's about 2.5 feet of water. So if we use water in here instead, it's about 2.5 feet is the displacement. So that's, you know, something on the order of something like this. It's quite large compared to, you know, a little bit less than a meter, right? Well, actually, something not right here. No, I'm sorry. My bad. This is about 2.5 feet. Mercury would be about 2.5 feet displacement, okay? Water is about 30 feet of displacement. If you were to do the same calculation using the density of water in here instead, you'd get something on the order of 30 feet, so substantially larger. That's be a very large barometer you'd have to measure the atmospheric pressure, right?
Yeah.
Yeah. Now, I'm just going to put mercury, Hg for mercury here. Anyone remember what Hg stands for? No, it's mercury, but I mean, what is the Latin word for mercury? I forget. I used to know. You remember? No? Okay. So, atmospheres, pascals. Right, so it's about 100,000 pascals is atmospheric pressure. Another measurement unit is a bar. 1 bar is approximately 1 atmosphere. So it's approximately 100,000 pascals. I think that's all the units that I wanted to put up there. But we can, of course, modify this barometer, right? And we can do something different with it. If instead I cut the top off this tube, now I have P naught on this end, right? And let me connect it to a box with an unknown pressure, right? So this could be a gas cylinder. You've seen these gas cylinders before, right? They contain nitrogen or helium, for example, right?
Yeah.
So I hook that up to the end of this. This is now called a manometer, I believe. U-shaped manometer, I think, something like that. But so this can measure pressure. This time we have P naught on this side, right? And we have some unknown pressure here, right, in our gas cylinder, for example. And we can measure delta P is called the gauge pressure. That's what you would measure if you were like measuring the pressure in your tire, right? When the tire goes flat, it'll read 0. But of course, that's not really the pressure because you still have atmospheric pressure around. So if the tire is flat, the inside the tire is still at atmospheric pressure, right? It's not like you evacuated it, yes? And so the pressure gauge reads what we call gauge pressure. It's just delta P, okay? And that would use the same formula we had over here, right? It's rho G times delta H. So whatever delta H is, right, that tells you what the gauge pressure is, okay? Now, in this configuration, if I want to get the absolute pressure, all I'd have to do is solve. Delta P is going to be P minus P naught, right? the atmospheric pressure. So this is equal to P naught plus rho g h. And that's our absolute pressure. Okay? So you increase the pressure in here, right? It's going to push the liquid down, cause it to rise up over here. Remember, the liquid is virtually incompressible. So if this is a uniform tube, however much it goes down here is what it's going to go up over there, right? And the difference between the two levels, delta H, is, well, it's equal to the weight of the displaced liquid. Okay? That's an important thing to think about, especially getting ready for our next lecture, which will be Archimedes' principle, or buoyancy. Okay? So what is this saying? It's saying that the displacement, right, the pressure difference between this part and this part here is just compensating for the weight, right? Because if it was perfectly balanced, the weights balance out, right? So the delta H, right, is defining this little volume here, right, from this point up to here, up to the top, right?
Yeah.
And so that has some amount of weight associated with it, right?
Yes.
And so delta P is what is accommodating that imbalance, okay?
All right.
So think about that. Does this make it? Yeah, I know there was some question. I got the feeling that yesterday's lecture did not come across as well as I thought it would. There seemed to be some confusion there at the end. So hopefully, now that you think about this, right, you can just simply, if we want to go back to what we were talking about yesterday, instead of talking about pressures, right, imagine putting a weight physically on top of the liquid, you know. And we're going to ignore the fact that it may sink into the liquid a bit, right? But if it didn't, if we had some absolute way to, you know, seal up the container as we push it in and just push it down to some level, right? But with zero friction, then it would have to support that weight, and that weight would be pushing down on the liquid, right? Mm-hmm. Yeah? So, I think that's all I wanted to say about measuring pressure. Does that make a bit of sense?
Yeah.
You get the idea?
Yes.
Yeah? Any questions on how barometers work? The various units for pressure?
No.
Really only use atmospheres when you talk about atmospheric pressure. So if I said, what's the pressure, atmospheric pressure on Mars, I might report it in atmospheres, right? But if I were going to talk about the pressure inside of a, gas cylinder, I might use torr, millimeters of mercury, which are the same, or I might use pascals, okay?
All right.
But for physics, usually we use pascals, because that's the SI unit, newtons per meter squared. Okay?
Okay.
That's it.